So last time we proved this theorem showing that the probability of Clique number being smaller than k is extremely small. And here k is defined in this way. So we consider this f of x, which is the same as the expectation of, so in here we are thinking about this in for g and half, the random graph. And this f is expectation of number of x clique. So k0 is the point where this expectation is as close to 1 as possible. It's either k minus 1 or k0 minus 1 or k0. And then let k be the value which is smaller than k0 by 4. Then this shows that with high probability, we must have a clique of size at least k with the probability which is 1 minus this. So now we want to use this to prove the following theorem by Borlobas. So with high probability, we have that the chromatic number of G is more or less n over 2 log 2n. So this is theorem by Borlobas. And actually it took quite a while since the question was raised until the Borlobas finally proved it. For the lower bound, it's not difficult. Both lower bound and upper bound are not difficult, but the lower bound was known much before, and upper bound was proved by Borlobas. And if you consider independent set of G and Clique number of complement of G, they have the same distribution. This has, what I mean is this has the same distribution with just considering the Clique number of G, or G, say drawn from this random graph. Because, this probability space, if you take the complement, it has the same distribution as the original one. So, from here, what do we do? If we take, say, k0 plus 10, then f of, say, k0 plus 10 is smaller than or equal to n to the, say, 1 over n to the 9. Plus, say, real of 1, more or less. Then from this, we said that this is the expected number of k0 plus 10 clique. And which is smaller than this number. So from that, use the Markov inequality, that the probability that the omega of G bigger than k0 plus 10 is smaller than this number, which goes to 0. So with high probability, we know that the omega of G is upper bounded by this number. And because the alpha of G has the same distribution as the omega of G, independence number has the same distribution as a Clique number. So we know that the independence number of G is also, upper bounded by more or less K. So which is 2 plus, we know that K or K0 or K0 plus 10 or have this form. So it's n mod 2 plus log of 1 times log sub 2n. Then lower bound is easy because we know that the chromatic number is lower bounded by n over its independence number. Because chromatic number is, if you have a graph G, you want to partition it into chi many independent sets. And each independent set has size n mod alpha. And then all of them together has n mod n vertices. So we get this inequality holds. And upper bound in the independence number yields this. So this holds with high probability. So once that happens, then we have this lower bound. So this lower bound also happens with high probability. So now we want to show upper bound. And how do we want to show upper bound is that we have a graph G. And what's our goal? We want to partition it into independent set. And the number of independent sets is not too many. That's what we want to ensure. So what we do is we take an independent set and then take out. And the remaining graph, we take an independent set and take out. We take an independent set and take out, and so on. We want to do that. But at some moment, if the number of remaining vertices is too small, then we don't know whether we can take a large independent set. We want to make sure that each independent set is large. So that we do that. And if very small number of vertices left, then we just give new colors for each one vertex. And then we want to wish that until the almost last end, we want to make sure that the independent set here has size more or less this. And the number of remaining small number of vertices is observed into this log of 1 term. It's smaller than n over log n. So that's what we are hoping for. For that, what do we have to do? After deleting certain vertices, so we take out this independent set, and then in the remaining one, we should be able to take out next independent set, which has size almost this number. So we want to show that every not too small set contains an almost optimal size independent set. That's what we want to prove. And that set, which is not too small, the size must be quite smaller than this, so that all the remaining vertices, we give the new color, different color for each vertices. The number of colors we use are bounded by this log over 1 times n over this logarithmic term. So for that, we define this m, which is smaller than this number. And we want to show that for any set S of m vertices, we want to be able to find an independent set inside of S, which has almost optimal size. For that, we want to study the induced subgraph induced by this S. Then for this, the induced subgraph, say G bracket S, we know that this has the same distribution as Gn, not Gn, Gm half. Then let K be K0 m minus 4 as before. So remember this K0 was actually a function which satisfies this relation. when this is n. So we replace this with m, then you get the new function f, and with that function f, you can compute this k0. But again, I mean, even if we replace n with m, this equality still holds. We still have k being 2 plus log of 0, log of 1 times log sub 2n. Then, now we use the previous one. So we know that it has with high probability it has not too low Clique number, and then because Clique number and independence number has the same distribution, same inequality holds for independence number. Then we know that the independence number of this induced subgraph being smaller than k is smaller than e to the negative c times m squared over log 4m. Wait, why log 4? Log 8. Sorry. Let me go. Log 8m. And this is for specific s. But the number of such set S is at most n choose m, which is smaller than n to the m, which is smaller than 2 to the m log n, which is smaller than 2 to the n over log n. We have that the probability that alpha of g s is smaller than k for some s of size m is you take the union bound, you have at most this many choices of s, and each of them we have the probability c m squared over log 8m. And what's m? M was taken to be n over log square. So if you just apply to here, then this is a bit smaller than linear, and this is a bit smaller than log quadratic. So you can easily show that this goes to 0 as n goes to infinity. So from this, what we know is that with high probability, we can say that every set of size m contain an independent set of size k. So now we suppose that G has this property. Then what do? We have a G, and because of this property, we can take any M set. Then in that any M set, we can find the set of size k, which is independent set. Then we take out an independent set of size k, and we take this as a color class. And what we do is we just repeat this until, how much can we repeat? Until there are less than m vertices left. So as long as there are, the remaining set has size at least m, we can do this. At the end, what we do is then we give each remaining vertices a distinct color. Then what we do is the number of color class we get is n minus m over k plus m, which is m of n over k plus m. And again, k is roughly 2 log n, and m is smaller than n over log n. So this is n most n of 2 log n times 1 plus 3 log 1. And as this happens with high probability, and once that happens, we have this upper bound. So this upper bound also holds with high probability. So with high probability, we have, lower bound and upper bound. So it is indeed more or less n over 2 logs of 2n. So this shows that the chromatic number of a random graph is concentrated around this number. So with high probability, you take a random graph, then you can actually predict the chromatic number. And moreover, if P is, so we consider G and half, which is a special case of G and P. And we can consider other P, and then we can ask the similar question. And for other constant value P, we can actually, do the similar technique. So with some modification, you can actually prove related, result. You can, do it as an exercise. But of course, if this P is a function of n, then the statement becomes a bit, the proof becomes a bit different. And in some sense, it gets easier if P is much smaller. So if P is much smaller, we can even get a better bound, better concentration of the chromatic number of this G and P. So we want to show this theorem. When P is n to the minus alpha, with alpha being bigger than 5 over 6, and let's say this is a fixed constant, alpha is fixed constant, that G is drawn from G and P, then there exists U depending on n and P. So that with high probability we have the chromatic number of G is between U and U plus 3. So it's either U or U plus 1, U plus 2, U plus 3. In other words, if you consider G and P probability distribution, and here all possible graphs are here with certain measure. And if you take all the collection of graphs with the chromatic number being U, chromatic number being U plus 1, chromatic number being U plus 2, chromatic number being U plus 3, then this actually take the almost all measure. The remaining, this part, the measure of this goes to 0 as n goes to infinity. That's what this means. So we want to, prove in a way a bit similar, not similar to the before, but the similar philosophy. So before we show that every set of size m contains an independent set, and we keep taking out, and the remaining thing we color it in an arbitrary way. So here we want much better concentration. So in a sense, we want to color most of them, and then remaining one, we want to color it with the constant many number of colors, say 3 colors. So somehow what we want to do is we want to color as much as we can with the U colors, and then remaining one, we want to color it with, say, 3 colors, and most 3 colors. Then we can make sure that the number of colors that we need is between U and U plus 3. That's roughly how we want to do. So for that, we want to again show that this remaining thing can be colored with at most 3 colors, as long as this remaining set has not too small size. That's what we want to claim first. So fix any constant C, then with high probability, if n is large enough, every C square root of n vertices of G, which is drawn from G and P, can be 3 colored. Is chromatic number 3. So I mean, this statement, if you make it rigorous, then fix C, and for epsilon given, if n, there exists n0 depending on C and epsilon, so that if n is bigger than n0, then I mean these vertices can be 3 colored with the probability at least 1 minus epsilon. So you should be able to, I mean, write it in a rigorous way if necessary. But as we have been well trained on the how to, I mean, write things rigorously and what this means when we use this notation with high probability, or almost, I mean, asymptotically surely or almost surely, then I mean we know what it actually means in a rigorous sense. So let's just write it in this way. So this is what we want to prove. So what we will do is, if a graph cannot be colored with 3 colors, then I mean we know that if it cannot be colored with 3 colors and it's minimal in that sense, meaning that it's a critical graph, color critical graph, then we know that it must contain at least certain number of edges. If this is too sparse, then it's easy to color. So by using that, we want to show that all small set has at least certain number of, I mean, at most certain number of edges. Then this can be shown. So roughly, we want to show that every small set contains not too many edges, so that the obstacle of coloring it with the 3 colors are not there. So let T be a minimal set that is not 3 colored, not 3 colorable. Then the minimality, by the minimality, every vertex in T has at least 3 neighbors in T. It's easy to see that if X has 2 neighbors, then this is smaller than T, so this can be colored with 3 colors. And this is red, this is blue, then we color this with the 3rd color, then you can extend this coloring to finish the 3 coloring of every vertex in T, which is a contradiction to the assumption that T is not 3 colorable. So G induced by T must contain at least 3T over 2 edges, where T is the number of vertices in T. So now we consider the probability that there exists a set T with at most 6 times square root of n vertices. having at least 3t over 2, say 3 times size of t over 2 edges is at most the following. We take the, what am I writing? So if the set T has 3 vertices, then it's always can be, it's always 3 colorable. So we take the T between 4 and C times square root of n. The number of possible sets T is n choose T. So you have a T vertices. And then you compute the probability that it contains at least 3t over 2 edges. Then you want to find the upper bound of this. So this probability can be bounded by you take the all possible 3t over 2 edges among these t choose 2 pairs, and then all of them are edge. The probability is 3t over 2. So this is inefficient upper bound, but it is an upper bound of the probability that this specific set T, which is fixed by this many choice. Once we fix this, the probability that it contains at least this many edges is upper bounded by this. Then this can be rewritten as, by using nt is at most ne over t times t, to the t. So we use this inequality. Then you have this. So p is n to the negative alpha. So you use that, and you use this inequality for those 2 binomial coefficients. Then you do some computation, then you can actually get this. But alpha is bigger than 5 over 6. So this is strictly negative. So this is smaller than, not just smaller than 1. Each term is n to the sum minus epsilon, which goes to 0. And then even if you do this geometric series, then this is still real of 1. So this proves the claim that with high probability, every vertex set of C times square root of n vertices can be 3 colored. So now we want to, show the existence of U. And for that, we want to use the Azuma's inequality in the following way. So let epsilon be positive, which is arbitrary. Then what we want to do is that we want to show that if n is large enough, then we have chromatic number of G between U and U plus 3 with probability at least 1 minus epsilon. Let's just say 3 epsilon. So it's same. Epsilon, 3 epsilon, that's not really important here, but in the later proof, the numbers are better if you write 3 epsilon. So how do we do it? Is we let U be the least integer so that probability of the chromatic number smaller than equal to this u is actually bigger than epsilon. So as you lower u, this probability keeps decrease. At some moment, at the last time it's bigger than epsilon is u, but if you go one more, then the probability becomes smaller than epsilon. So such u must exist. Now we let y, which is defined by this random graph G, be the minimal size of a set of vertices S, for which G minus S is U colorable. So again, if you have G, if this is already U colorable, then we don't have to delete anything. But if it's not U colorable, then you consider the minimum number of vertices, where once you delete this, then rest can be colored with U colors. Then this is function defined on this random graph. And this random graph is actually considered as a, concatenation of this collection of independent random variable. So for each pair, it's either 0 or 1, 0 or 1, 0 or 1. So, n choose two distinct, mutually independent random variables forms this random graph G. And this y is defined over this, this independent random variable. And once you change one coordinate of this, then, y value changes at most 1. More, specifically, you can consider this as a vertex, vertex Lipschitz. This can be considered as a vertex Lipschitz. So you actually, as I mentioned, this G, random graph G, is same as a collection of independent random variable. And you consider the gradation so that every time you reveal the edges between the new vertex and then next vertex. So this edge forms a B1, and this 3 edge forms B2, and then this 6 edge forms B3, and B5, and B6, and so on. With that, if you change, all the edges incident with one vertex, then YG changes at most 1. In here, if you have a vertex and then you change some edges incident to only with this vertex, then, this may have to be deleted or not deleted. So this Y value doesn't change more than 1. So this satisfies vertex Lipschitz condition. As the changes on the edges which are incident to one vertex it may change YG by at most 1. So, we consider the vertex exposure martingale. And let mu be the expectation of y, which is same as y0. Then you apply the Azumas inequality. Or here, if you say, technically what we are using is the lemma we showed last time, this one. You can show that it's lower than its expectation by lambda square root of n, is at most e to the negative lambda square over 2. And probability that the y is bigger than mu by lambda square root of n is smaller than e to the negative e square over 2. And here let lambda be the number such that e to the negative lambda square over 2 is same as epsilon. So you solve this, then you can actually give some value to lambda satisfying this. So now what do we know? What was our definition of u? We have this, right? That was the definition of u. Here, this is the probability that y of g is 0. So if entire graph G is U colorable, then Y of G is U. Y of G is 0. You don't have to delete anything. So this is bigger than alpha. This is bigger than epsilon. So what do we know is that the probability that Y is smaller than mu minus lambda n is smaller than epsilon. The probability of y being 0 is bigger than epsilon. So if 0 is smaller than this number, then we would have inequality here, which yields a contradiction. That means 0 is actually bigger than this number. So this shows that mu is smaller than lambda square root of n. It must be. Then what does the second inequality become? Probability that y is bigger than 2 lambda square root of n is actually, because mu is smaller than this, so this has a smaller probability that y is bigger than mu plus lambda square root of n, which is epsilon. So this happens very rarely. So with probability at least 1 minus epsilon, there exists U coloring of all but at most this much. So this epsilon determines lambda. So this is some constant C prime. At most C prime square root of n vertices for C prime, which depending on epsilon. Then we use the previous claim. With probability 1 minus 0 of 1, every C prime square root of n vertices of G can be colored with 3 colors. I mean, it might be more intuitive to you if we use, so we work it out, the value of C prime, and with that C prime we use this claim. Now we know that every this many vertices can be colored with 3 colors, and you use this argument to show that with probability 1 minus epsilon, there exists a U coloring of all but this many vertices, but we already know that these vertices can be colored with 3 colors because we show that that holds for every, this many vertices. Hence, we know that this holds with probability at least 1 minus epsilon minus 1 0 of 1 is 1 minus 2 epsilon at least. for large n. Again, but minimality of u ensure that it's at least u with the probability 1 minus epsilon. So together we have that the probability that this chromatic number of G is between u and u plus 3 is at least 1 minus epsilon. So as this epsilon can be arbitrary, we know that the chromatic number of G is one of these 4 numbers with high probability. And it is actually known that if alpha is bigger than half, then chromatic number of G is concentrated on at most 2 values. And if you think about it, these 2 values is best possible. Because let's say in N, G and P, you know that, most of the graph have a chromatic number U. And you increase this by 1. Then it could still be that the most of the graphs satisfy this equality. And you keep increase this n by 1. Then at certain point, this chromatic number should grow. So at certain moment, it should be that now the next value is taking up most of the space. But right at the time, so between say G and 0 P and between G and 0 plus 1 plus P, intuitively, it's unlikely that this is U and this is U prime 1, U plus 1 at one moment it was almost U, but it was now U plus 1, because this U is roughly, you can, it depending on P, but it's roughly like logarithmic order. So changes of 1 here is unlikely to make this jump all the way to U plus 1. So there must be some, intuition, our intuition tells that there must be some state that, many are U and also many are U plus 1. And then this and this, both of them are non-negligible for certain range of n. So you maybe, hopefully this can convince you that this 2-point concentration is best thing we can get. But more generally, for not so small p, let's say Gn half, it is recently proved by Haeckel that chromatic number of Gn half is not concentrated on fewer than n to the quarter minus root of 1 consecutive integer. So we cannot hope for like this strong concentration that there are a small number of values that this chromatic number is one of them. So you need to, it could be that it's one of these, at least n to the 1 over 4 many values. So this is about the chromatic number of random graph. And then in the next video, we will start considering about the concentration around the median instead of the expectation.